kilometres. Its velocity is 4,800 metres per second. Determine the gravitational force required to keep this satellite in orbit. Alright, let's have a look at it. The gravitational attraction between the Earth and the satellite must provide sufficient centripetal force to maintain the circular orbit. So we must convert, so basically, we have the Earth here, we have the satellite here. There's going to be a force of attraction between those two. Okay. If there's a force of attraction between those two, if it's stationary, they're going to draw together and it's going to be a nasty mess. But because there is circular motion of the satellite around the Earth, then what that means is the force, basically, it's falling towards the Earth and the Earth keeps moving out of the way. And it goes through from... so in order to get the unbalanced force required to keep that satellite in that orbit as opposed to going off tangentially, those two are going to match. So we must first convert the altitude to an orbital radius. So the orbital radius is the altitude plus the Earth's radius, and we get as much as that, and it's going to be 1.738 by 10 to the 7 metres. Now your centripetal force, if you go back and have a look at that, the centripetal force is equal to mv squared on r, and so we find out there that in this case the centripetal force is going to be equal to approximately 6,900 newtons by using F equals mv squared on r. So we've got the radius and we've got the velocity that's travelling at. So that is the gravitational force needed for this satellite's orbit. Motion is approximately 6,900 newtons. We can check this answer by using Newton's law of universal gravitation to directly calculate the gravitational force that does exist. If you know the mass of the, so in this case, we know the mass of the satellite, and we know the mass of the Earth, and we know the distance between the two centres, then if we do that using F equals G m1 m2 on r squared, then what we're going to have is we should have a value of attraction that equals the same as that. Is it going to do that for us? There you go. And it works out to be approximately 6,900.
With that, could you just use the second equation? So use the gravitational constant equation instead of using the circular equation?
Yeah, you could if you knew the mass. I mean, you know the mass of the Earth, I suppose. There's no reason why you couldn't. But what this does show is that, well, if you were going to get a career launching satellites and you want them to be staying in orbit, and you know the mass of the satellite, then this allows you to work out the velocity that the satellites have to be moving at in order for them to stay in orbit. Okay. If they're going faster than that, okay, then if they're travelling faster, the centripetal force will be greater. And actually, if they're going slower, then they'll drift away. Okay. So remembering circular motion. Your centripetal acceleration is equal to v squared on r. So therefore, since force equals mass times acceleration, the centripetal force is going to be equal to m times v squared on r. And since we have the period, or the time it takes to do one circle, okay, well we know that the period is equal to the distance travelled divided by the velocity. Now we know the distance is going to be, well, that's r, then it's going to be 2 pi r on the velocity, so that v equals 2 pi r on the period. So in other words, the velocity of the object travelling around here is going to be the total distance that it goes, which is the circumference of the orbit, divided by the time it takes to do one orbit, the period. So you've got So, since centripetal acceleration equals v squared on r and a squared, we obtain a centripetal acceleration is equal to 4 pi squared on r on t squared, because we've just substituted the value for v straight back into that value there, and that's what we work out. So, and the centripetal force is equal to 4 by pi squared r m on t squared. Now, that's on your information sheet, you don't need to remember that, but you do need to be able to apply it. In other words, if you want to work out what the centripetal force of an object is, you need to know of an object circling another object, you need to know what the mass of that object is, and you need to know what the period is, and then you'll be able to work out the forces. And the radius, sorry, you also need to know the radius. You just need the radius and the period to find out what the centripetal acceleration is. So, radius of the Earth and the equator is 6.4 by 10 to the 6 metres, and its mass is 6.0 by 10 to the 24 kilograms. Calculate the centripetal acceleration at the point on the equator. There we go. If you're looking at it from that on, if you're standing up here, then in 24 hours you're not moving very far. If you're here on the equator, in 24 hours you're actually moving that whole distance. So therefore, if you're standing on the centre, on the equator, you're going to have some centripetal acceleration towards the centre of the Earth. Then we'll find out the centripetal force acting on this point and the linear velocity at this point. Okay. So your period, you know, is 24 hours. It takes 1 day to rotate, 86,400 seconds. So the centripetal acceleration is going to be equal to 4 pi squared r on t squared. Stick that in. And your centripetal acceleration standing on the centre there is going to be 0.034 metres per second squared towards the centre of the Earth. Now, the force that you're going to have at that point, the centripetal. Yeah.
Where did for the centripetal force, where did the 4 and the t squared come into?
That one?
Yeah, because before it said A equals v squared over r.
Okay, I'll rush through that a little bit. I'll go back and have a look. Now,
They just put in like the velocity.
yep, that's right. So we've obtained from the, we know we've got this from circular motion, we've got a squared, the centripetal acceleration is equal to v squared on r. Okay? If you multiply that by m, you get the centripetal force. So you get Fc equals mv squared on r. Now, went through and showed you that v is also equal. We've got the circle around that centre. Then the velocity at this point is equal to the distance that it goes divided by the period, and the distance that it goes is going to be the circumference of that circle, which is 2 pi r, divided by that. Now, if we just go equals, if we substitute in for the value of v into that one there, we get m 2 pi r on t squared all on r, which equals m 4 pi squared r squared on t all on r. That's going to cancel one of those out with that one, and we get equals 4 pi squared m r on t. It should be the same as over here. Squared. Sorry? That's better. 4 pi squared mr on t squared. Is that okay?
What happens to the mass as these are not valid?
What happens to the mass?
Yeah. Oh, okay, I can see that one. Let's sort that one.
Right. So we went past that, didn't we? Yeah. So the centripetal acceleration at that point is equal to mass times okay. So seems a bit odd. 6.0 by 10 to the 24 by 0.003 gives you 2.04 by 10 to the 23 newtons pushing in. And the velocity at that point is going to be the distance around the equator divided by the period. It's going to be 465 metres per second, which is why, so when it's zipping around that way, at that point you're actually moving at 465 metres per second, which is why the Americans, when they launch their rockets, they do it down here in Florida as opposed to up here in Maine somewhere. They go as far south as they can, so they actually get a head start from the rotation of the Earth. It's actually, if they're zipping up and putting them into orbit this way, then the fact that they're actually travelling, the further the equator, closer to the equator you get, the faster that your velocity is going to be in that sideways movement. So that's extra velocity you don't have to put in, which is extra fuel you don't have to pack. And that's why the Europeans, when they launch their rockets, they don't do it up here. They do it down here in Guyana, which is pretty much on the equator. It's about the optimal place you can have for launching a rocket. The Russians, they don't care, they just do it up here. They just crank that one up. Alright, have a go at question 21 on page 150 and use a value of R of 700 kilometres in that one. And I'll continue to look for these. Must have put